This is example problem 6.8. This problem statement says a solid 0.75 inch diameter shaft is subject to the torques shown. The bearings shown on the shaft or allow the shaft to turn freely. We're asked to find or to plot the torque diagram showing the internal torque in segments 1, 2, and 3 of the shaft using sign convention presented in section 6.6, and then determine the maximum shear stress magnitude in the shaft. So if we look at our diagram, right now it shows that this is right here y, and this is x. And if I go ahead and draw our diagram here with our x and y like this, then we'll have, we can just say we have A here, B here, C here, and D about here. So when it says that the bearings shown allow the shaft to turn freely, these are the bearings here on the ends. This bearing here and this one here. I'm not going to draw those on our diagram just because they don't resist the moment or the torque that's acting in the shaft, and won't help with computations. So if we remember the convention, sign convention from section 6.6, using the right hand rule, if we look at section 1 on this shaft, so at point A, at that member, if we're looking at point A with the right hand rule, this torque that's being applied is being applied in the positive direction, which means at point 2 that torque is in a negative direction, at point C positive direction, and point D is in negative direction. So looking again back at our diagram at A, B, C, and D, what I'm going to do is I'm going to go ahead and draw a free body diagram of each section. So I'm going to cut it here, and then I'll make another cut and draw another free body diagram and make a cut there, and then I'll do it a third time and we'll make a cut there. So let's do the first free body diagram, and I will show the member here. This is point A. There's a positive torque of 10 foot-pounds, and then to resist it there is another torque that we'll just call torque 1. So if we sum the moments about x, right, because remember our axis that I drew here, so this would be torque 1 and this 10 foot-pounds are acting in the x direction, right? So we'll sum our moments around the x. Sum the moments around the x equals 0. Right hand rule convention. So we have torque 1 plus 10 foot-pounds equals 0. So that means that torque 1 equals a negative 10 foot-pounds. So drawing the second free body diagram, we're going to extend this we have A, and then B, and A has 10 foot-pounds acting this direction, B has 50 foot-pounds acting that direction, and then there will be an unknown torque called T2 acting that way. So again, summing the moments about x equals 0. So 10 minus 50 plus T2 equals 0. So T2 then equals 40 foot-pounds. So again, what I'm going to do now is, I said earlier I'm going to make a cut between C and D, right? So if we look at our original diagram here, if I start from D and move inwards and draw a free body diagram of this, we can isolate that and separate it from the rest of the member. And that might be a little bit easier to help remember our sign convention. So our third free body diagram here with D has, remember, a negative 30 foot-pounds, right? So this will be negative 30 foot-pounds, and our T3. So again, summing the moments about the x direction equals 0. We get negative T3 minus 30 foot-pounds equals 0. So T sub 3 equals our torque equals negative 30 foot-pounds. So those are the torques, right, in each member. Now the problem asked to plot that in an internal torque diagram, right? So what I like to do is I've already drawn right here kind of a diagram up the top. So what I'll do is just kind of mimic this shape here, this length. And we found that the torque in member 1 is negative 10 foot-pounds, and the torque between B and C, so member 2, is going to be 40 foot-pounds, and then the torque between C and D is negative 30, right? So what I'll do is I'll start at A. We'll start at A, and we'll go down negative 10, and that's going to stay consistent for the entire length of member 1. And then when we get to B, point B, then it's going to be a positive 40 foot-pounds and it's constant until we get to member C. And then when we get to member C, it'll go and become a negative 30 foot-pounds until we get to member D. So this is negative 30 foot-pounds, negative 10 foot-pounds, and this is 40 foot-pounds. So if you think about this, let's look at our diagram again, the original one. And if we start at D, say I start at D and I walk along the member from D to A, right? We're walking in that direction. If I start at D, we have an immediate jump at D of negative 30 foot-pounds, right? And that's true on our diagram here. So it jumps to negative 30. It walks constant until we get to C. And then there's a positive 70 foot-pounds. And so from this negative 30 plus 70 is 40. And then that's constant again until we get to member B. And then that's going to be a negative 50 foot-pounds. So 40 minus 50 is negative 10, which is what we show here. And again, it's constant until we get to A. And then negative 10 plus 10 zeroes out at the end. And so this will be our torque diagram. So the next question says, determine the maximum shear stress magnitude in the shaft. So shear stress, as you know, should be tau max is going to equal the torque multiplied to C divided by J, where C is going to equal the diameter divided by 2, and J equals pi over 32 multiplied to the diameter to the 4th. So our diameter we know is 0.75 inches. So our C value is going to be 0.75 divided by 2. And our J value is then going to be pi divided by 32 multiplied to 0.75 to the fourth. And so for the entire shaft, these two values are constant because it's continuous. It's the same member, it's the same material, same diameter all the way through from member 1, 2 to 3. So for tau max, the only thing that changes is the torque at each location. So we'll say for tau max of member 1, our shear maximum shear stress, member 1 is then going to equal our negative 10 foot-pounds multiplied to 0.75 inches divided by 2 divided by our J value, which is over here. So we have pi divided by 32, 0.75 inches to the fourth. So if you noticed, we have a discrepancy between our units here. We have feet on this side and inches on this side. So we need to make sure that we have that conversion, 12 inches per 1 foot to get the units to match. And so tau max for member 1, if you punch this in, get it correctly, you should get 1,448.7 pounds per square inches, or we can say PSI. If you do the same process but use the different torque, right? So we used for member 1, right? Member 1 right here, we used the 10 foot-pounds. So for member 2, we're going to use 40 foot-pounds, and member 3, we're going to use negative 30 foot-pounds. So if you do the same computations for members 2 and member 3, for member 2 you should get 5,794.7 psi, and for member 3, tau max, you should get 4,346.0 psi. And the question asks for the maximum value, which is located in member 2, which makes sense because that's where our greatest torque is applied.